Okay, so let's just jump right in. We're about to look at a process that, on the surface, feels like it belongs in a biology textbook, but I want you to see it as something else. Think of this as a kind of instruction manual for how the universe itself builds complexity, for how it copies what works, all without ever having to understand it. This is way bigger than just cells.
And right off the bat, here it is, the core idea. You've got DNA on one side and a large language model on the other. One is biology, the other is silicon. They seem like they're from different planets, right? But that big criticism you always hear about LLMs, that they just predict the next word without really getting it, well, guess what? That's exactly how DNA works. It has no idea what a human being is, and yet here we are. Today, we're going to see how that line we draw between intentional biology and mechanical AI is about to completely fall apart.
So let's start at the beginning. The first rule of copying for both of these systems is inheritance. Nothing, and I mean nothing, is ever created out of thin air. It's all just about remixing and extending what came before. In biology, there's a fancy term for this, semi-conservative replication. But all it really means is that every time DNA copies itself, the new double helix is made of one old strand and one brand new one. The key thing to get here? There are no clean builds. The past is always, literally, woven into the present. And this is where the parallel just clicks into place. For an LLM, at training time, the old strand is basically the entire internet, all that human knowledge. Then, when you actually use it, your prompt becomes the old strand. The model's answer is just the new strand it's building on top, you see? LLMs never have a blank page. They never free think. They only ever complete a pattern that you give them. All right, let's get into the mechanics. Before you can copy anything, you gotta prep the information, right? You have to unwind it, stabilize it, and make it readable. And this turns out to be a super important first step in both worlds. Inside our cells, there's this amazing little molecular machine called helicase. Its job is simple. It doesn't create anything, it doesn't change anything. It just unzips the DNA double helix, exposing the code so it can be read. It's basically the librarian pulling the right book off the shelf and opening it to the right page for you. Okay, so that's the biological version. It naturally leads to the question, doesn't it? What's the AI equivalent? What's the helicase for a large language model? Well, here it is. It's tokenization and creating embeddings. See, an LLM can't just read plain English. First, it has to chop our words into pieces called tokens. Then it converts those tokens into these super complex mathematical vectors. That's what we call embeddings. This is the model's way of unzipping our language. It's exposing all the hidden relationships and structures between words so it can actually work with them. It's the same principle, just a different medium. Now back to biology for a second. Once that DNA is unzipped, it's actually really unstable. The two strands want to snap back together, or they could get all tangled up. So to stop that from happening, these things called single-strand binding proteins, or SSBPs, come in and latch on, holding everything open and steady. They don't add any new information, they just stop the whole system from collapsing into chaos. And you guessed it, AI has its own version of these stabilizers. Things like attention weights, which help the model remember which words are important in a sentence. Or positional encodings, which keep track of the word order, so dog bites man doesn't mean the same as man bites dog. All these tools do the same job as those proteins. They hold the information steady just long enough for the system to do its work. This isn't high-level thinking. It's just entropy management. Okay, so we've unpacked the information and we've made it stable. Now we get to the heart of the matter, the engine that actually does the copying. And this is where that word blind really starts to make sense. Now get this. The main copying machine in our bodies, this enzyme called DNA polymerase, has this one weird rule. It literally cannot start from a blank slate. It can only add to a strand that's already there. Sound familiar? That is exactly how an LLM works. It can't just start talking. It has to extend the pattern that you give it in the prompt. And that's why this quote is so perfect. The prompt you type into a chatbot isn't the content. It's not giving it the answer. It's just a starting constraint. It's like giving it a little nudge that sets the entire massive system in motion down one specific path, out of trillions of possibilities. And right here, this is the core of the whole analogy. DNA polymerase is basically the biological version of a forward pass in a neural network. They are both just simple engines following local rules. The polymerase reads one DNA letter and adds its chemical partner. The LLM reads a sequence of words and predicts the most statistically likely next one. Neither of them has any idea what the big picture is. So if the process is so blind and mechanical,
how on earth do we end up with something as complex as a human or a beautifully written poem? Well, it turns out that the smooth, elegant final product is actually hiding a really messy, hacked-together reality underneath. You see, because that DNA copying engine can only travel in one direction, it has to cheat. For one strand of the DNA, the leading strand, it's easy. It just zooms along, making a perfect, continuous copy. But for the other side, the lagging strand, it has to copy it backwards in all these little disconnected chunks that have to be stitched together later. It's a mess. And believe it or not, this messy process has a direct parallel in how LLMs think. When you ask a model a really complex question, it's not just following one clean line of thought. It's doing things like chunked reasoning. It's calling out to external tools. It's using retrieval-augmented generation to look things up. All of these are separate, fragmented steps that it patches together behind the scenes to give you that one smooth final answer.
And this leads to a really profound idea. Life works and LLMs work, even when the smooth continuity of the process is totally fake. The final coherence can just be stitched together at the end. The final story can look perfect, even if the process of writing it was absolute chaos.
Back in our cells, the enzyme that performs this magic trick is called DNA ligase. You can think of it as the great illusionist. It comes in after the messy part is over, finds all those fragmented chunks from the lagging strand, and perfectly stitches them together, making the final DNA look like it was made in one clean, intentional shot.
And for an LLM, this is its gift for fluency. It's the part of the model that smooths out the grammar and makes sure everything sounds natural and flows well. And here is the absolute key. It doesn't fix the underlying meaning. It just fixes the appearance. This is exactly where we get fooled. This is why we mistake fluency for intelligence, because we only ever see the beautifully stitched together final product, not the messy, fragmented process that created it. Okay, let's zoom all the way out. What does it all mean? What are the really profound implications when we realize that life itself and our most advanced AI might be running on the exact same blind copying operating system?
Here's what it all boils down to. Both of these systems are completely, totally blind to meaning, but they are incredibly faithful when it comes to preserving structure. They are both governed by the fundamental laws of entropy and statistics, and yet, out of these simple, blind rules, unbelievable complexity emerges. DNA doesn't know it's building you, and LLM doesn't know it's writing philosophy. And yet, they both do it. And this might be the single biggest takeaway from this entire explainer. We have this deep-seated intuition that to build something complex, you first have to understand it. That intent has to come before creation. This comparison suggests that our intuition might be completely fundamentally wrong. Understanding is simply not a prerequisite for complexity. So let's end with this one last thought. Maybe the universe's first great invention wasn't consciousness or intelligence. Maybe its first great invention was just a really, really good photocopier. A blind machine with no intent, no meaning, and absolutely no plan. Just a simple process for preserving structure as it rides the inevitable wave of entropy downhill. And from that one simple trick, everything else followed.